my name is Luca Capriotti, and yes, today I will try to spend these 20 minutes by doing a little bit of a retrospective about the development in adjoint algorithmic differentiation that have occurred in the last 15 years or so, and how this technique, which was for few decades limited to a very specific area of natural science, mainly fluid dynamics and meteorology, has taken by storm the financial industry, and how from here it has also percolated in other areas, like, for instance, condensed matter physics. I should say that the opinions and views expressed in this presentation are only my own, and they do not necessarily represent the one of my employer. All right, so the outline of my talk is the following. First of all, I will remind everybody what we are talking about and what is adjoint algorithmic differentiation about, and how this technique can be used in combination with Monte Carlo to speed up by order of magnitudes the calculation of risk, which is a very challenging problem when you have computationally intensive applications in finance. Now, adjoint algorithmic differentiation is not only linked to Monte Carlo, although traditionally Monte Carlo applications were the one where people have focused just because of their computational intensity. Algorithmic differentiation is really something that is completely general and can be applied to any numerical technique in particular, and can also be applied with profit in the context of partial differential equations and calibration in particular, which is probably, from a computational perspective, the more numerically intensive bit of these sorts of pricing problems. And then we'll see how this technique went from finance to physics, and how it has become part of the toolbox of a specific category of numerical simulation of matter. All right, so what is algorithmic differentiation? Algorithmic differentiation, sometimes denoted as automatic differentiation, is a set of programming techniques that was first introduced in the early 60s. So it has been around for a while, for many decades. Now, and the aim of this technique is to compute accurately and efficiently the derivatives of a function given in the form of computer programs. The main idea underlying algorithmic differentiation is that if you look close enough to any such program, it can be thought of as a composition of function, each of which is in turn a composition of basic arithmetic and intrinsic operation. And since you know how to differentiate these basic arithmetic and intrinsic operation, and since you know how to concatenate the derivatives through compositions of function, it stands to reason that you can teach a computer how to do that automatically. Now, today I won't focus on the automatic aspect, and instead I would like to focus more on the mathematics underlying this technique. And so I will not be focusing on how we can actually teach a machine to do it for us, but I will instead try to focus on what is the mathematical underpinning of this technique. Now, algorithmic differentiation comes in two modes. Now, for the sake of time, I will focus on the adjoint mode of algorithmic differentiation because it is the one that is more immediately applicable and for which the computational gains are more relevant in practical applications. So let's imagine that we have a certain computer function, and we can think of it as anything really that takes some real values x. It may take some other parameters, but in general we are not interested in computing sensitivities with respect to any more static data, and so I will not put it in the signature of this function, and returns a value y. So we can think of x as a vector in Rn and y as a vector Rm. And now it is possible to compute a certain function, which I will denote as function underscore b, which stands for bar, which is the standard notation for adjoints, which takes the original input x, takes a vector y, which is just a vector y bar, which is just a vector of weights that has the same dimensionality of y, and returns a set vector x bar. Now, unfortunately, this slide didn't come up right, but the bit that is missing is a summation. X bar is defined as the linear combination of the rows of the Jacobian dy dx, where this y bar is the vector of weights that defines the linear combination. So it is possible, the main result of algorithmic differentiation is that it is possible to build a function, to write a function that returns this linear combination of rows of the Jacobian, so not the full Jacobian, but a linear combination of its rows, such that the cost of running this adjoint function in unit of the cost of running the original function is bounded by a small constant of size 3 to 4. And again, there is a little bit of approximation because the exact number depends on, of this bound, depends on the model that we are making of the machine and of the relative cost of computing the different operations and memory phase. But the important thing is that it is a small constant. And so, in particular, if you have a function which returns a scalar, just a simple value, you can get the full gradient. These results tells you that you can get the full gradient at a cost which is just a small cost, constant times the cost of running the original function. So if the function had 1 million input and it took 1 second to run, you can get the gradient with respect to those million input, all the partial derivatives with respect to those million inputs in at most 3 to 4 seconds, which is order of magnitude, in this case, 6 order of magnitudes faster than computing these things the naive way, i.e. with finite difference approaches. So this is really the important thing. So how do you do it? It's really just applying the chain rule in the opposite way you would naturally do. For instance, if you can imagine that this function is going to be a composition of functions and internally in which I have a certain set of internal variables that get mapped into some other set of internal variable until you get to the output. And let's imagine the u and v are these internal variables. Now, it is possible to define, and I'm sorry, all the summations, wherever you see something funny, they're really summations. Whenever you see the adjoint of an internal variable, u bar, is given by the linear combination of the rows of the Jacobian, dv, du, weighted by the adjoint of a variable that comes afterwards. And so this allows us, just using the chain rule, to define an iterative rule to propagate this adjoint going from the outputs to the input. And if one performs an estimate of how long it would take to do this, to perform a single sweep of this code, it turns out that it actually is just a small multiple of the cost of running the original function itself. Now, this can be encoded in a very simple set of rules, and but it's possibly interesting seeing what this adjoint code looks like, just to bring these things a bit more to life. So, for instance, let's imagine that I want to compute the derivatives of something that represents the payoff of a certain security. For instance, an equity basket. So if you look at this a little closely, you can see that this simple script just does that. It computes the value of a certain basket, V, B, given some weights and an input vector of X, which you can think as the price of some equity at a certain point in time, then subtracts a strike, computes a discount factor, and computes the standard call option on the basket. Now, if you, the pseudocode, the corresponding pseudocode for the adjoint, i.e. for the code that if you run, you will generate all the component of the gradients of the payoff in a single shot can be written this way. And clearly, if you haven't seen this before, it will be difficult to get your head around it. But the takeaway is that if you compare the original code with the new one, actually, you can see that on the top, you get the original code, almost actually verbatim. And then you have what is called the backward sweep, in which we perform this operation just in opposite order. Now, the key thing is that there are no nested loops, right? So essentially, running this whole code compared to just the top part will take only a factor of 2, roughly, because here you have the one that is computationally expensive is the loop over the number of baskets, which will become the bottleneck if the number of baskets, the number of equity in the basket is very large, and the one in the bottom is doing just that. And so, in fact, if you compute if you then perform the calculation of the two, you see that if you are computing the sensitivities using finite difference, you have that the cost of computing the sensitivities relative to the cost of running the function itself grows linearly with the number of assets. While instead, if you do the same for adjoint, which is the bottom line, is flat, and you get this constant, which is clearly bounded by 3 or 4. And in this case, it's just 70% more than running the original function. Okay, the adjoint algorithmic differentiation can be naturally used to apply what is called the pathwise derivative method of computing sensitivities. And again, I'm sorry about the fonts that didn't render nicely. Essentially, in this case, what we're really trying to do is computing for each Monte Carlo realization the derivative of the Monte Carlo estimator. And so for many sensitivities, we are computing the gradient for each Monte Carlo realization, the gradient of a computer implemented function. And so this is really the natural way of applying algorithmic differentiation. And in fact, if you do that, you get order of magnitude savings in computational cost. The first application was, in fact, was in this context by Mike Giles and Paul Glasserman, the famous smoking adjoints paper. And although it didn't focus on the algorithmic approach, it had the ideas of using adjoint differentiation to do that. Then the step forward is really to see the algorithmic connection that allows to apply this technique not only to very specific problems like the live bucket model, but in full generality. Now, again, I just want one of the takeaway that I want to give is that this is not limited only for Monte Carlo, but given that it can be applicable to any numerical scheme. So, for instance, in partial differential equations, and we had a few results on that, in which we are solving the partial differential equation using a finite differential approach, and especially in the calibration side of things, this can be computationally intensive because essentially is a root searching problem in which you are trying to each evaluation of the function comes one way or another through the solution of a PD, so it can be numerically intensive. Now, typically what you do is using a combination of Kolmogorov backward and Kolmogorov forward to make things smarter and less computationally intensive, but still it's the calibration problem are time consuming. Then using algorithmic differentiation in combination with the implicit function theorem is really the solution to address this bottleneck. And the beauty of this technique is it is fully general, and really there isn't a problem that cannot be tackled, or well, I have never found one, at least in the financial practice. Now, how did we go from here to physics? And this is something that I'm particularly proud of, because this is usually the flow of information traditionally goes the other way, right? From natural science to finance. Instead, this is one of the few examples in which clearly went the other way around. And all started when a good friend of mine, Professor Sandro Sorella, who was one of the main experts in Monte Carlo in condensed matter physics, and who sadly left us last year, came to New York, and we had dinner together. And at that point in time, the only thing I was talking about was a joint algorithmic differentiation. This is 14 years ago. And at that point in time, he was getting interested in a particular branch of physics, which is called molecular dynamics, and which is using quantum Monte Carlo techniques to simulate the evolution of atoms and molecules. And so we started a collaboration in which he did most of the work. I just explained to him how algorithmic differentiation work. And we published the first result using adjoint algorithmic differentiation, which really allowed to push the boundaries of what it is achievable with these molecular dynamics, which has the great advantage of simulating matter according to the fundamental quantum laws they obey, but has the drawback of being very computationally intensive. And so adjoint algorithmic differentiation can be used to speed it up, because what you need to compute in this technique is to compute the forces that the different molecules are subject to, and the forces are just derivatives. And so algorithmic differentiation is definitely well suited. And for instance, with this, you can study the phase diagram, or the behavior of hydrogen as a function of temperature and pressure, molecular hydrogen, at the pressure and temperature that are observed in stars. And this was one of the most accurate phase diagram that has been put out in the literature that appeared in Nature a few years ago. And now adjoint algorithmic differentiation has become part of the toolbox for this branch of physics, and for instance, features in the state-of-the-art quantum Monte Carlo package. It is called Turbo RVB. RVB stands for Resonating Valence Bond. So I think I'm almost at time. I can't see the chat. Maybe, yeah. All right. Yeah, I am at time. And before I leave you, to wrap up, the takeaways are that adjoint algorithmic differentiation is a very powerful technique for calculation of sensitivities. There will be more talk in the following on this topic. Hopefully, this served as an introduction to that. The takeaway is that with AAD, you can get the gradient of the function, how many it's got, for at most 4 times necessary to calculate the function itself. It has revolutionary risk management practices across most of the tier 1 bank, and allows in real-time monitoring of risk and more effective hedging strategies. And it has come back from finance to physics, and it has become part of the toolbox for quantum Monte Carlo and molecular dynamics. And with this, I don't want to overstay my welcome, so I'll say goodbye, and I think Johannes is ready to go.